screen share first. We'll go with the textbook here. And let me move this. This is what I should have done before I started the recorder. Gotten all this stuff moved around, which you can't see, but I have to do it. I'm going to also move you a little bit to the right. In fact, I think I'll move us up top. Okay, that way we're out of the way some. Okay, well, where we left off last time, if you don't have any problems or questions, where we left off last time, we're in Chapter 2, First Order Differential Equations in Section 2.6, the last section of this chapter. We're doing a numerical method, and the method we're going to look at is Euler's method. Now notice the title of this is a numerical method. Okay, this is just one. There are many others out there. Most of them these days are completely computerized, and you really don't have to know what they're doing and how they're doing it, but it's usually, excuse me, I got hiccups or something. It's usually a good idea to have a clue of what's going on with them, so that if they start giving some weird, bizarre, and seems like they're out of track, out of focus answers, you'll know indeed you're right. Okay, Euler's method is not a precise method. There are better methods than this, but this is one of the earlier methods, and it's amazingly pretty good under certain circumstances. Okay, so here I guess we'll just launch into it. I was hoping more people would show up by now, but they haven't yet. So what we did last time, we looked at a procedure for approximating a solution to an equation, a differential equation that we can't solve. We don't have the tools. There's no analytical method for solving that differential equation. And so to generalize the procedure just illustrated, we use the linearization of the unknown function y at some point x equal x0. Okay, so here's what we know. We know the initial value, and this truly is an initial value now. We know whatever this function is here, there's your solution curve. This, when x is equal to x0, y is equal to y0. So we know we're on the curve right there. Okay, now what we're going to do here is pick an h. That's the step size. You know, we used to talk about delta x's when we were talking in terms of derivatives. Okay, and this is a lot like that. But even before we did derivatives, if you remember at the pre-calculus, we had h being just a little bit, we use that same letter here, a little bit of a deviation from where x was, x plus h, a little bit to the right or left. We're going to take h being positive, so it would be to the right. Okay, so since it's a first order differential equation, we can write it in what they call the, it's not standard form, I don't think, maybe that's what they call it. dy dx is equal to some function of x and y. That's this, f of x and y. Okay, now that's what your differential equation is. That function, the dy dx, is equal to that function of x and y. Now we're going to evaluate that function of x and y at that one particular point that we know right here is x0, y0. And that gives us, and what is dy dx? That's the slope. Okay, so that gives you the slope of the tangent line right there. F of x0, y0, the slope of the tangent line right there. Now, just looking at this, that's a pretty good approximation for that function value all along that area here, region here, where the red line and the blue line almost seems like they're on top of each other. When you make your h over here, so your next step is further out, you've deviated from that pretty much. That's given you an error. Okay, here's where the function really is at x1. Here's where your linear approximation told you it was heading at x1. Okay, so you see we have a little bit of a discrepancy there. Okay, but that's not all the linearization. We use the point slope formula to say that the y, this is your y value, L of x, y minus y0 is equal to the slope times x minus x0. So this is your proposed new y value. So what do we use? We use that known value. F at x0, y0, that's the slope, times x minus x0, that's how far, that's your h right here. How far x has gone to the right from x0, that's your h. So multiply that slope by your value here and add the y0 to it. That brings you up to your y1. Now you see that isn't the same as what y1 really is. That's your estimated y1. There's your real y1. When x is equal to x1, here's the y equal y1. So that is your error there. Okay. Now, if we let h be a positive increment of x, okay, in the x-axis, that's what we're showing here, then replacing the x by the x here with x1 is equal to x0 plus h, which is what they show here. Your x1 is x0 plus h. So replacing this generic h here, x here, with that, you notice your x0s disappear. And what you have? The linearization here is equal to y0 plus h times f of x0, y0. That gives you your first y approximation. Okay? Then, and that's what it shows here, except they're putting the f of x0, x1, y1 here. I think it's a little premature, not immature, premature here. This y1 is your linearization of x1, which would be this part here. So I think those should be 0 subscripts there, not 1s. Okay, that's your y1. That point x1, y1, okay, on the tangent line is an approximation to x1, y of x1. So this point is an approximation to that point, okay, on the solution curve. Of course, the accuracy of that approximation, it depends heavily on the size of the increment. If you choose a much smaller h, then your error would be much less, okay? But if you're going some distance away, like maybe to find the value at the point up here, say, if you choose a real small h, it's got lots and lots and lots and lots of steps to get there. But you'll get there closer than what you do if you take big h's. Even though it won't take as long to get there, you then have bigger errors. Okay? So that's the exchange, the payoff. Okay? The point x1, y1 on the tangent line is approximately, so I think we got all that. Okay. So what we usually do is take this step size to be, quote, reasonably small, repeat the process using a second tangent line, this time at x1, y1. Okay. Well, how did we get our x1? They never, well, here it is. It's your x0 plus whatever your step size. So there's your new x1. Here's your new y1. These are supposed to be x0 and y0 here. That's your new y1. And then increase the x by h. That gives you x1. That gives you your y1. Go at it again. And again. And again. Okay? So let's scoot on down here to this. Okay? So you obtain an approximation y2 is about equal to y of x sub 2, corresponding to 2 steps of length h for x0. So x0 is equal to x1 plus h, and that would be x0 plus 2h. Now, I don't know why they brought that into play. You very seldom use it. They show it here, but that's what it approximates to be. So here is your recursive formula. Y sub n plus 1 is always y sub n plus h, your step size, times f evaluated at xn, yn. That's your slope there. Okay? And that procedure uses successive tangent lines. It's called Euler's method. Okay. Now, here's example 1. I'm going to scoot it up here so we can see it a little more clearly maybe, but what I'm going to do is go right into our calculations and we'll do these steps. Okay, so first thing I'm going to do is repeat that recursive formula there. So let me go to, glad you're here. I'm sorry you're the only one here. I don't know where the rest of them are today. So let's go to the whiteboard. Usually somebody's here by now, especially those who were here before. So what I'm going to do is move this taskbar kind of up and out of the way as much as I can. I will move us back to the right, okay, and I'll move the whiteboard to the left and up as far as I can to get me the maximum amount of white space. So here we go. Now I'm going to write down the recursive relationship again. So y of n plus 1 is equal to y of n, y sub n, that's not of n, y sub n, plus your step size times your f, which remember is the function value to the right of the equal sign. That is your slope, evaluated at x sub n, y sub n. Okay, now that will represent Euler's method. So here's our problem. Y prime, this is our differential equation, is equal to 0.1 times the square root of y it erases something whenever it wants to, plus 0.4 x squared. Okay, with the initial condition that y at x equal 2, y would be 4. So this is your x sub 0, and this is your y sub 0. Okay, now it says use Euler's method to obtain an approximation for y at 2.5. Now I'm not sure we'll go that far, but we'll head in that direction. Okay, first we're going to use h is equal to 0.1, which is a fairly small step size, but not super small. And then we'll do it where h is equal to half that size, 0.05. It'll take twice as many steps for the small steps to get from x equal 2 to x equal 2.5, but we'll get there more precisely. Okay, so this is now, this thing right here is your f of xy. That is your right hand side. That's what your derivative is. That is your slope. Okay, so we'll start with doing y1 when n is equal to 0 is equal to y sub 0. Okay, y sub 0 from up here is 4 plus, and we'll first use this one, 0.1 times now I sort of hate it. You have a 0.1 here as your h, you have a 0.1 which is part of your y prime, so don't get them confused. That's a 0.1 times the square root of 4, which is 2, because the square root of y, okay, that's a 2 there, plus 0.4 times x squared. Well, x was 2 squared, so that's going to be 4. Alright, so this is going to give us our y prime, or y1. So it's going to be 4 plus, okay, now I need another parenthesis to close that one out. Okay, this one is not too bad, so I'll do it mentally, but after a while we're going to start using calculators. Okay, this will be 0.2 plus 1.6, okay, so this will be 4 plus 0.1, that's supposed to be a 0.1, times 1.8, seems like we got that before, so this is 4 plus 0.18, so that would be 4.18. No, yeah, 4.18. 4 plus, oh, here comes somebody, I can't see who. I think it must be James. Good deal. Let me get James here, hold on a moment. He's connecting to audio now. So here's James. So we got 1 and 3, still missing 2, 4, and 5. Okay. I'm sorry, I'm starting this awfully soon now. Lunch sort of reinvigorated me a little bit. But now I'm running sort of low on energy again. Okay. I think I've got both of you here. They're here. Let me just check and make sure nobody else is waiting. No, they're not. Okay. All right, James, we are doing example 1 on page 78. We're chapter 2, first order differential equations, 2.4, a numerical method. We're using the Euler's method. And this is example 1, kind of in the middle of page 78. Okay. If I could get that window to go away, I would show you what your differential equation is. Y prime is equal to 0.1 times the square root of y plus 0.4 times x squared. There it is. Okay. And this is the recursive relationship for Euler's method, which we'll be using. Our initial condition for this differential equation is when x equal 2, y is equal to 4. So this makes our x0 2, the y0 4, and we're trying to head toward the y value at 2.5. Now, we're first going to use a step size of 0.1, which is sort of a large step size. It doesn't sound like it, but it is. Then we're going to do 0.05. This will take us 5 steps to get there. This will take us 10 steps. Okay, that, remember, is your f of x, y, and here's what, that's right. Oh, here comes somebody else. I think it's Ryan. Okay, let me see if I can let him in. I think it let him in. So let me, yep, he's coming in. So the top part of the alphabet is here, 1, 2, and 3. We're missing the bottom part, 4 and 5. Hopefully they'll be here. They were here earlier at Cal 3, but not here yet. And since they've heard all this, Ryan, this is mostly for you, and it mostly affects my office hours. And I hate to miss office hours, but I know this week I'm going to miss them. And for James and Kira, there is a new bit of information I did not know this morning, so I'll fill you in on that as well. For the others, they'll have to pick it up on the YouTube video later. Okay, but they were here this morning, so they've heard it. Ryan, two things happened last week. One started actually the week before. I guess I'll start with the one that started the week before. The Friday before last, I went in for blood work because I was going to see my hematologist for my leukemia. I knew the counts were going to be high because the last time I had a treatment was January of this year, and usually we have about 2 or 3 treatments a year. This will make only the second treatment in the year, so I knew my counts were probably going to be high. They were a little high back in June when I had a visit, late May, early June, sometime like that. And the doctor, because COVID was so running rampant at that time, he didn't want to bring me in. They weren't excessively high. They were about 19,000 where normal was 11,000. So that's not too bad. I've lived with that many a time. So he didn't want to do treatment then. I was all in favor of that. But since it's been 4 or 5 months since then, I knew the counts were going to be considerably higher than 19,000. I wasn't expecting them to have gone to 137,000. Okay, so they are a bit high. And because the white cells are so many, they're probably crowding out and messing up the production of red blood cells. So my hemoglobin's low, my hematocrit's low, my red blood cells are low, my everything is low. My platelets are low, and my white cells are through the roof. So my doctor is a bit concerned. The monoclonal antibody I've been using is very effective. It's been in the past. No reason to expect it's not now. But because the counts are so incredibly high, more than likely it's going to release a whole bunch of junk into my blood system as it destroys these white cells that have the marker on them that indicates the malignant cells, and it's going to probably wipe out bunches of those at one time. So in doing that, they're going to put me on I can't think what you call it, a thing to help flush my system out. There's a name for it. I can't think of it now. I'm going to start that tomorrow. And this is the part that's new for the rest of you. I did get a phone call in between my last class and this class when I was downstairs. They do want to start the treatment this Thursday, and that's the whole reason to tell you all this. That they're going to have me go in at 7 o'clock Tuesday morning, and they're going to do a 10% dosage, but they're going to do it incredibly slowly to make sure there's no negative reactions. And they say that's probably going to take most of the day. They're going to allow 8 hours for it. I hope it won't take 8 hours. So if it goes 7 in the morning until that would make it 3 in the afternoon, I think would be 8 hours. It would be. If I can get away from then, I hope I'll be back home shortly, hopefully before my 3:15 class starts. And hopefully I'll be in here and be able to teach that 3:15 class. However, they give me Benadryl and all sorts of things that make me really groggy, and if you think I'm bad here, just wait until Thursday. That's probably going to be pretty bad, but I'll see if I can hang in there and teach that class. Okay, why am I telling you all that? Well, that's on top of something else. Last week I had a very good friend. She's a 76-year-old woman. Was in our Sunday school class for a couple decades now, maybe longer. Just a real sweet lady. She had problems. She was mentally ill, something on the spectrum between bipolar and schizophrenic, and but she fought with it and dealt with it and lived with it as best of anyone I've ever can imagine doing. So anyway, she collapsed after a Bible study at church last Tuesday evening, was rushed to the emergency room. They got her to intensive care after several hours of stabilizing her, and she stayed there for 2 days until she died. So she died on Thursday. I'm her contact person. She had no living family here in Alabama. She had no contact. If she had any family, closest sister was in Virginia, but that sister was quite a few years older than her, if she's still alive. We don't even know that. But Judy had no contact with her for, as far as the decades that I've known her. I never heard her say she had any communication with any family member whatsoever. I know her parents both died. She was the youngest in the crowd. She was a surprise baby very late in their marriage, and so she had her parents long gone, and her sister may even be gone. And I think any older siblings were probably, and here comes Miguel or Jesus. So we got 4 out of 5 here. All we're missing is Jemanuel. Okay. Hopefully he'll be coming in. And he's heard all this before, or most of it before. So anyway, on top of my having treatment this week, I'm now having to deal with, in some small way, organizing 2 memorial services, one at our church and one at the Episcopal place where she lived. I'm responsible for getting her apartment cleared out, though the people at Episcopal place are going to help big time with that, which is I'm very thankful for. Also, she was an artist. A lot of people in the church didn't even know that. So we're going to be going Wednesday afternoon. A guy from church is going to go and take pictures of her artwork, also furniture and stuff like that. So if any of the ministries of the church need any of the things in her apartment, we can get them to them. The artwork, so members of the church can have things to remember her by. So there's all that to do. So what this boils down to, and this morning, let's take this morning for instance, from 8 to 10 I had office hours. I'd say probably 40% of that time I actually got work done for the college. The other 60% I was on the phone with either the chaplain or the people at Episcopal place, or she left her body to science, so the person at UAB. It was one thing after another. I got a few emails cleared. Some of those dealt with Judy, some of them dealt with work. So that's how it's been. That's probably somewhat how it's going to be this afternoon, so I hope I'll be able to get more work done than I will having to mess with the other, though I know I've got a couple emails to answer there. Okay, so this afternoon, say again? Oh, so well, thank you so much. I really appreciate that. So here's the bottom line. Office hours a day from 4 to 6. Hopefully most of it I can spend in office hours, but I know there'll be some things I have to deal with because I can only catch these people when they're at work, and when they're at work, I'm supposed to be at work. So anyway, there's that. So I'll have to answer a few emails dealing with that, but the rest I'll try to do work stuff. Tomorrow, the only office hours I have are between 1 and 3. I know the chaplain at Episcopal place is going to call sometime in that time frame, and I will need to get with her and make some arrangements there. Hopefully she's going to do most of it, but I'll have to coordinate with her. That's all I got on Tuesday, and hopefully that won't take all those 2 hours or part of those 2 hours. Okay? Wednesday in the morning, hopefully I won't have too much time occupied with this, so I should have most of my 2 hours, 8 to 10 in the morning. However, my 4 to 6 on Wednesday afternoon, completely gone. That's when I meet with the guy from church to go over and get pictures of all her work and her furniture and that kind of stuff. So that's those office hours gone. And then, as I found out today, Jesus and James, I don't know if you're here to hear it earlier, they have called in between Cal 3 and this class. They called and let me know they have scheduled me for infusions 7 o'clock Thursday morning. So I will be over there from 7 at least until 3. If I can get home by 3:15, I'll try to meet with my late afternoon class, but I'll lose my 3 morning classes, my pre-calculus algebra, pre-calculus trig, and for 3 of you, the different linear algebra. Those will be gone Thursday. I'll be here tomorrow, but not Thursday. Okay, almost certainly. And then Friday, when I have 4 hours of office hours from 8 to 12, completely gone. My appointment there is at 8:15, so I have to leave here by 8 o'clock, and that's going to be a 90% dosage, so that's going to be probably 8:15 until at least 4 o'clock, probably more like 4:15 or 4:30. Could easily be there till 5. So Friday is wipe slit. So part of tomorrow's office hours, I know I'll be tied up. The rest of it, hopefully I'll be there. Most of this afternoon's office hours, I hope to be able to spend at work. Wednesday morning, I hope to spend most of that at work. Wednesday afternoon, none. Thursday, none. And Friday, none. Okay, so this week, office hours wise, the first part of the week, mostly. Last part of the week, absolutely none. Now, next week, hopefully most of this will be winding down. However, she lived in a HUD-supported apartment, and HUD's rules and regulations are that everything has to be cleared out within 2 weeks. So she died on Thursday of last week, so I've got until Thursday of next week to have everything out. But like I said, Episcopal Place is going to help with that big time. I just have to sort of be the contact person. I'm going to try to do that as much as possible from a distance, because I'm not supposed to be around people, especially just after having treatment. I'll probably be more anemic than I am now, and I'm already very anemic. And so I need to be really protecting myself as well. So anyway, we'll see. After that, hopefully I'll be on the mend and everything else will be winding down. So just to let you know what it's going to be like for a bit. Okay, now what we're doing, for now that everybody's here, we're doing Euler's method, example 1 on page 78. We've done the first step. We found our y1. We are estimating now when h is equal to 0.1, x would be 2.1, and y would be 4.18. So guess what? This is our new y1, and x1 is equal to 2 plus 0.1. So this will be 2.1. So what do we do from here? We come up with an approximation for y2. And y2 is going to be the new y1, 4.18, plus, now this 0.1 is our h here, so that doesn't change, 0.1, times, this 0.1 is part of our function value. That's also not going to change, 0.1 times the square root of 4.18. I can't do that one in my head like I did last time, so we're going to have to work that one out, plus 0.4, now that's part of the problem up here, okay, times x squared, and that's 2.1 squared. So that's going to give us our new y2. Okay, I'm going to reach for my phone, which is acting as my calculator today most of the time. It's fully charged again. Gotta log in, go to calculator mode, and since I'm going to be doing square roots, I'm going to turn it sideways so I can do scientific mode. So let me see if I get this right now. 4.18, 4.18. This has tiny little buttons. I have big fat fingers. Okay, plus 0.1 times open parentheses. Okay, 0.1 times, now on this calculator I have to do the 4.18 before I take the square root. So 4.18, take a square root of that. That's why I need it in this mode. Okay, plus 0.4 times 2.1 squared. Close parentheses, and I think I press equal. Yes! Okay, so that gave me a y2 of about 3.4. Okay, I'm going to write down a bunch of digits. 4.376845. Now, I usually would not use that many digits, but because anytime I round off, it's going to exaggerate the error. Let me make sure I got it right. Okay, so that's our new y2, which will make now our new x2 to be, with a step size of 0.1, this will be 2.2. Just add another 0.1 to that one. Okay, so that leads to my y3. What's my y3? It's my y2. Oh, let me make sure I'm on the money in the book. 4.3. They rounded 4.3768. Yeah. Okay. So that would be my y2, which is 4.376845. Now, normally I wouldn't carry around that many digits, but I'm going to do it now. Plus 0.1, that's your step size, times 0.1, that's from your problem up here, times the square root of this y2, which is 4.376845, plus 0.4, I forgot to close off my parentheses here, 0.4, that was part of the problem up here, times your x, which is now 2.2 squared. Okay, and that's going to be what I use to calculate y3. So I've got my y3 on my screen now, so I'm just going to add to that plus 0.1 times, open parentheses again, 0.1 again, okay, times, now I have to enter my number, and this is where I'll probably screw up, 4.376845, so I've got some round off there, take a square root of that, plus 0.4, that was part of the problem, times 2.2 squared, close the parentheses, equal. Okay, and that gets me up to, I hope y'all are doing this with me, approximately 4.6. Now I probably shouldn't round that much, but I just hate carrying all these digits. I'll carry them. 4.591366, because the next digit's a 9, I'll round that to a 6, and hopefully that will be okay. What did they get? 4.5914. Yep, that's what we got. Okay, that's your y4. and I mean y3, and the x3 here is just 2.3. All you do to that is add the step size to it each time. So now your y4. So you see the pattern here and what's going on? Do you need me to keep doing this? Do you see how it works? And again, I left off this parentheses. I did it on my calculator, fortunately, but I need to write it in there. Maybe I should make those brackets. This is the one that closes that off, because these two work right here. These two just enclose that number there that you're squaring. Okay. Now, do you want me to show another step? Are you okay with seeing how this works? Anybody? Does anyone need another step? Okay. I hear none, so I'm going to assume that means we're okay. So that being said, I'm going to clear this off the screen. Once I do, I don't want to bring it back. Clear that and go back to there. Now, I'll just write down from the book what they got for 2.4. They got a y of 4.8. I'm skipping all the calculations, just giving you the answer. 4.8244. Okay? And then when they went to 5, y sub 5, which would be, now you're up to 2.5, which is where you're wanting to go. If I can get my pen to show up. That's where you're wanting to go. So when when your step size is 5, that was 0.1, you started at 2, you did 5 steps there. The first was 2.1, 2.2, 2.3, 2.4, finally 2.5. That's what you're looking for. That y5 was, I should have approximately equal to, but I have equal to 5.0768. Now, here's the problem, folks. Okay? As far as I know, we don't know the exact answer to that. Okay? So we don't know how close we are, whether we're there or not. Okay? But just hang on to that. That's your 5.0768. Okay. Now, I'm going to erase all this, and we're going to start working on it when we have the 0.05 as our step size. Okay? So let's clear the drawings, and I'm going to repeat what I said before. Okay? Your y of n plus 1 is equal to y sub n plus, now your step size is 0.05. That's where the h went. Times, now this 0.1, that's the one that was part of your problem. Okay? Times the square root of your y. Okay? Plus 0.4, wasn't it? Yeah, 0.4 x squared. Okay, so that was our issue here. We're starting the same place. I don't know what those sounds are. I don't know if y'all are chatting. That's fine if you do. If I'm supposed to respond to a chat, please let me know. It could mean I'm receiving an email, which is not surprising either. Okay, so in between classes, I was able to take care of a couple of emails, and they're probably responding to them now. This is school business. Okay. This is assuming, remembering our y prime, which is your f of xy, which is, in this problem, this thing right here that we had, 0.1 square root of y plus 0.4 x squared given y at 2 is equal to 4. This gives you your x0, y0. Okay, so we'll go straight to our y1. That's equal to the y0, which was 4, plus 0.5 times, maybe I should put that as a bracket, okay, 0.1, that was part of the problem. Square root of 4 is 2, I can do that one, plus 0.4 times your x was 2, squared would be 4. Okay, so there is going to be your y1. Now I can do, well, let me use it on the calculator. Okay, I don't need it on this one. That's 4 plus 0.05. That didn't write too well, did it? I didn't realize that. 0.05. Okay. Okay. 0.05 times open, oh, this doesn't have open parentheses. I've got to turn it this way, okay, because that has open parentheses. 0.1, I should have done that one in the head, times 2 plus, and I can do this one in my head, 1.6, close parentheses, equal 4.09. Okay, and that's what they got. Your y1 was 4.09. Now, corresponding to that, your x1, remember, is not as big as it was before. This is 2.05. You're just going up one step size. So let me erase this because that was just an extraneous mark that showed up. Oh, here comes your manual. Fantastic. All right, I hope you hadn't been waiting long. Okay, let me set this aside for a moment so I can mark them here. Way to go, team. This is a happy, happy day for me because we have perfect attendance all day long. 4 people in my first class, 8 people in my second class, 5 people in my third class. Perfect attendance all day long. Makes me feel warm and fuzzy inside. So way to go, folks. And Emmanuel, I think you heard all of the sad, strong. The only thing you didn't hear, they have scheduled me for treatments this Thursday and Friday. I didn't know that in my Cal 3 class, but when I went downstairs to finish up lunch and recharge some fluids and also go outside for a bit with my dog, they did call. I was in the office with my wife. She wanted me to review something for her, and the phone rang, and it was the clinic, and they want me there at 7 o'clock Thursday morning, and they said they've set aside at least 8 hours. I hope I'll be home before 3. If I am, maybe I can get my afternoon class in. However, I may be drugged with Benadryl. It's going to be fun to see if that's going to work. But we'll go with that. But my morning classes probably are not going to make. Okay, I'll be tied up with the infusion basically all day on Thursday up until hopefully I'll be back by 3:15. So my morning classes wipe slick. Hate for that to happen, and I'll tell all of them that tomorrow. Hopefully I'll get my afternoon class in, but then on Friday I will be all day. They aren't going to start me till 8:15 on Friday, so That means, and that one will almost certainly go 8 hours, so that'll be at earliest 4:15, more than likely 4:30 or 5 before I'll be out of there. So my entire Friday is wiped out. So just a quick synopsis here. This afternoon's office hours, hopefully I'll be available for most of those. Tomorrow's office hours between 1 and 3, I think a fairly small phone conversation with the chaplain at Episcopal Place. Hopefully we'll get everything worked out there. So the rest of that time I should be in office hours. Wednesday morning, hopefully most of those first 2 hours, 8 to 10, most, probably not all, but most, hopefully I'll be able to do work. And then from 4 to 6 though, definitely none of that, because I'll be at Episcopal Place with the guy from church, taking pictures and that kind of stuff. Then I have to do that when the people are there, staff is there at Episcopal Place, so I've got to do it before they leave. Okay, then Thursday, like I said, I'm going to be leaving here probably 6:45 in the morning, maybe a little before that, getting to the Clarkin Clinic and in the infusion clinic from 7 until at least 3 probably, or it's close to 3. And then then I may make it back in time for my afternoon class, but I won't have any office hours left. Whether I can make a 4.5 hour class, then I don't know. We'll try. And then on Friday, completely out of the picture, because I'm in the clinic from 8:15 until probably 4:30 or 5. And so I'll have to leave here by 8 o'clock. So my entire Friday is gone. So anyway, that's where we are. That should open next week up a little bit though. We'll see. All right, let's get back to example 1. We're doing the calculating our Y2. Now our Y2 here is one step size away from what is equivalent to our Y1 when we did 0.1. Here we're doing point. So this is taking our 4.09, our Y1 4.09, plus the 0.05, this keeps doing that, times 0.1, and that's from the problem, and our new x1 is 2.05. Wait, that's not right. The square root of 4.09, and I don't believe that is 2.3, but we'll see in a minute, plus 0.4 times, and this is our 2.05, 2.05 squared, close parentheses, and see what that will yield. Okay, so let me get my calculator back on. Okay, there was my Y1 4.09. I'm going to have to turn it sideways to get it to scientific mode. So that plus 0.05 times, open parentheses, 0.1 times 4.09, because I have to enter the argument first, then take a square root of it, and that is not 2.3. If you were thinking it was, it's not. Okay, plus 0.4, part of the problem, times 2.05 squared, close parentheses, equal. That gives me a 4.18, approximately 4.18. Okay, now looking above, that is very close to what we had there. It's not just 4.18, it's 4.184161 0.8742. Now you don't need that many digits, but I just wrote them down. That's your y2. Your x2 would be 2.1. Okay. So this is a little bit greater than the 4.18 that we had when we were one step size away before. That was at 2.1. Now we're at 4.8 with this decimal after that. So let's move on to y sub 3. And that would be that y sub 2. I'm not going to write it all down, but I've got it here on my calculator screen. Plus 0.05 times, open parentheses, okay, 0.1 times, okay, now I've got to type in all those numbers, 4.18416.187.42. I don't need that many. Take the square root of that, add it to 0.4, that was from the problem, times 2.05 squared. That didn't work. It's probably going to come out a wrong answer. 2.05 squared. Okay. Close parentheses and hit equal sign. Hey, I think it did work. No, it didn't. Yeah, it did. Pretty close anyway. I may have punched in a number wrong because my calculator did mess up on me there. That I got about 4.27844. Okay. See what the book got? 4.2826. Now I may have made a mistake on my calculator. That could have happened. But they did round off earlier than I did. So I don't know. One of those is the thing. But rather than waste too much time doing it and checking it out, let's see what we've got. Your x sub 3 would then be 2.15. Okay? And then the y sub 4, I'm not going to do the calculation because I may have made a mistake on mine. I'll use the one they got in the book, 4.2826. No, that's the one we just did. 4.3854. And your x sub 4 would then be 2.2. So if you look at the one above at 2.2, that was 4.3768. This was 4.3854. So you see we're getting a little bit closer to what the actual curve probably was. Okay. Now, does anyone need me to go any further? If you carry it on out, you see ultimately the final answer. Last time we got 2.50 was at 5.0768. This gives us 5.0997. Now that sort of would make you think maybe the answer is near 5.1. I bet you it's a little bit larger than that, but there's no way that we have to do an exact calculation for that because this is not solvable. That differential equation is not solvable in any technique that we have. So that's what we got. Any questions on that before we go any further? Let's go out of this mode and back to our book. If I can get my screen share to show up here. and these are the tables that we were just looking at. You see the 2.0, that was where we started. 2.1 up here was at 4.18, 2.1 here, 4.1842. Not a lot of difference, but this is a little bit greater. 2.20, 4.3768, here 4.3854. Okay, I hope I was looking at the right table before. 2.30 here was 4.5914. This is 4.6045. Still not a lot of difference, but you see you're getting a little bit closer to probably what reality. 2.4 here was 4.8244. This is 4.8423. So it's inching on up there a little bit. Let's just scoot down a little bit here. The 2.50 up here was 5.0768, down here 5.0997. Okay. Excuse me just a minute. I need another sip. Beginning to lose it. Okay. Maybe that'll get me through. Okay. We got just under 15 minutes. Do we? Yeah, that's right. Okay. So that ended example 1. In example 2, we apply Euler's method to a differential equation for which we know the solution. We do this to compare the values of the approximation y sub n at each step with the true or actual values of y sub n of the initial value problem. So here is our problem. Now I'm going to move y'all out of the way. Move you back to the top. Okay. You can't see that, but you are blocking my view. Here's example 2. Okay, consider the initial value problem y prime is equal to 0.2xy. We've actually had this one before, okay? And actually what we're going to do, let's first solve it exactly, just to see what we've got, okay? And we'll do at y1 equal 1, and we will do it. And then we're going to try to get to x equal 1.5 from x equal 1, first in steps of 0.1, then in 0.05. We're not going to do all these, but we're going to get them started. So let's go to the whiteboard, and it's okay to clear this out of the way. Also, I'm going to move Miguel or Jesus out of the way too. All right, to clear? Okay. So here's our problem. Y prime, okay, y prime, which is dy dx, is equal to 0.2, this is ugly writing, xy, and your initial value when x is equal to 1, y is equal to 1 also. Okay. Now, we're going to get the Euler's method in a minute. Let's us first do it. Okay. Now remember, y prime stands for dy dx is equal to 0.2, so ugly, xy. Okay, with that initial condition. So let's rearrange this and solve by separation of variables. That would give us a dy over y when we divide both sides by y. That wipes out the y here, and that's equal to, and multiply, so to speak, write it in differential forms and put your dx over here. So that would be 0.2 x, because we divided out the y, dx. We separated the variables. Integrate both sides, and this will be log of y is equal to 0.2 times x squared over 2 So this will be, yuck, 0.1, okay, x squared. And then we'll evaluate that from, well, let's write it. Let's both sides, okay? So that would be y is equal to, okay, 0.1 x squared to the, okay, I'll have that. We're eating both sides, x squared, and we'll evaluate that from, where do we say, 1 to 1.5, isn't it? I think so. I didn't write that down. 1 to 1.5. Okay. Okay. So that will be y is equal to, okay. Now, actually, they're going to do it step at a time. So the first time it's going to be 1 to 1.1. Next time 1 to 1.2, 1 to 1.3, 1 to 1.4, then finally 1 to 1.5. Then the next time they'll do it 1 to 1.01, 1 to 1.02, 0.5, 1 to 1.1, 1 to 1.15, 1 to, yeah, they're going to do it in steps there. But this is what we get, and let's just do the final answer. That's e to the, let me see if I can get that in there. Whoops. How are we doing on time? Yuck, I'm running out of time. Got to do it in this scientific mode. Okay, so I've got to start with this. I'm going to do 0.1 times 1.5 squared, okay, equal, and then raise that to the e. I've got to find it here. I know it's on here somewhere. I can't see it. I see the E down here, but I don't think that's the, oh, I know what's wrong. I'm in second mode. E to the X, there's where I got it. Okay. Whew. All right. So that's when E evaluated at that point, minus 0.1 e to the x equal. Okay, so I get that answer, the final answer, y at 1.5, I got to be approximately 0.14715 18. Okay, let's see what they got. Make sure I did it right. The actual value, no. Whoa, couldn't be. Yeah, I did something wrong, terribly wrong. Sorry, but we don't have time to find it, I don't think. Yeah, we got 3 minutes. Well, oh, I see. I'm sorry, I made a mistake here. I should have, well, this part is wrong. This should have been just saw it 0.1, and this should have been x squared minus 1. Okay, and I didn't get that right. Sorry about that. Okay, and we really don't have time to do very many of them, but let's get it set up anyway. Okay, here is our Euler's method. Y to the n is equal to y to the n minus, okay, how did they do it? They did y to the n plus 1 here. It's equal y to the n plus, and then the step size 0.1 times this thing here. And this thing here, this one right here, is 0.12, no, I can't read my writing, 0.2 xy. Okay. So this would be y sub n plus 0.1, this keeps writing poorly, 0.2 x sub 1, which is 1.1, no, we're doing the first one, just 1, okay, 1.1, okay, times x, which is also, no, x was 1 and y was 1 also, okay. So that's a pretty simple multiplication there to do, okay. And let me see if I can do that real quickly. Your 1 is, y1 is 1, so it'd be 1 plus 0.1 times 0.2 times 1 times 1 times 1 equal 1.02. And that's what they got for y sub n, 1.02. So this is y sub 1, 1.02. That's equal to your y sub 1. Okay, so you take that and put it in, so y sub 2 would be equal to y sub 1, 1.02, plus 0.1 times 0.2 times, and I didn't write it down here, x sub 1 would equal to 1.1. Okay, that would be 1.1 times y sub 2 is 1.02. Okay, we've just gone over. So if you follow that on out, you'll see that you get a value about 1.0424 and keep going, whereas the actual value was 1.0450. Well, you keep processing there, and you see your absolute error actually increases incredibly slowly, but it does. Your relative error, though, increases just a little bit faster. Of course, relative error, we'll talk about that next time. So I don't know where you're going to want to begin that next time, but let's basically talk about relative error and percentage relative error. We'll do that next time. We almost finished, folks. We almost finished 2.6. All right. Homework exercise here. Do either one. It should be at it should be in the back of the book if it's in the back of the book. Do number 3 if it's in the back of the book. It says use a numerical solver in Euler's method on any of the odds 5 through 9. We'll see if you can do those on your own and go with that. Try to do number 11. That should be in the back of the book too, and you can stop there. Now, here's my question to you. Do you want me to go on and post the second test? I know some of you have submitted your first test, so do you want me to go on and post the second test so you can start working on it, even though we're technically not through with 2.6 yet, but we will be through early on Wednesday. Okay to go on and post it, or would you rather not even look at it yet? Okay, I hear no comments, so I'm going to go on and post it. If you don't want to look at it, you don't have to. Okay, so we'll do that for before Wednesday. So it'll probably be posted under week, whatever this is, 10, is it? Week 10 assessment, which I'll change to be test 2. Okay. And then I'll also probably put it on, if I can't put it there, I'll definitely put it on Blackboard Message. That's where I'll put the test for sure. If I can, also put it under week 10 assessment, which I'll rename to be test 2. Okay, so you can get it either place. It's more convenient for you to get. When we actually finish the section, I'll give you a few more homework exercises you can do if you wish to, the chapter 2 in review. And that's on the next few pages. So any questions now? Sorry we ran out of time. Sorry I spent so much time talking about my situation, but I thought y'all needed to know in case you were looking for me and couldn't get me. I didn't want you in the dark of why you couldn't. All right. So if there's no more comments, are there any? And I'm going to stop sharing. I'm sick and tired of sharing. Appreciate your being here. Perfect attendance again today. Way to go. So I'll end the meeting unless there's any last comments. Anything from anybody. Take care. We'll see you, some of you tomorrow, 3 of you tomorrow, and all of you on Wednesday. Take care. Bye-bye.